This is a Bomem DA3 Fourier transform infrared spectrometer, one of the very best high-resolution spectrometers you can get your hands on, even today, 40 years after it was built. And this particular one is on loan from Mike down in Austin, who has a business keeping these things going for research institutions all around the world that are still using these to do real deal science. So thank you, Mike, so much for this opportunity to get hands-on with this thing and learn more about this field of spectroscopy. But because I like doing things in hard mode, we're going to be doing this as if though it really were 1985, which means that we have the full original card cage up here with all of the original cards, and we're going to plug this thing into a PDP-1173 that has a high-performance vector processor bolted to the side of it. But what is spectroscopy, and what makes this one so special? Well, it's essentially all about light, or more specifically electromagnetic radiation, but I'm going to keep calling it light because electromagnetic radiation is a mouthful, and sitting alone in a room talking to a camera is already weird and hard enough as it is. I don't need to make it harder on myself. But essentially we have a light source that is generating light, and that is passing through a seemingly complex collection of mirrors until it strikes an object under test. Now this can be an oil or a liquid or a thin film or pretty much anything that will allow some of that visible or infrared light to pass through it. Then we have a detector on the other side of that object that detects the total amount of energy striking it. And this can tell us a huge amount about what molecules are making up that object. But there is a key missing component here, because if that light is just passing through, there's a massive amount of different wavelengths in there, and we need to be able to differentiate those wavelengths from each other. The light passes through this kind of insane looking piece right here, which is called a beam splitter, and it does what it says on the tin. It splits the beam of light. Half of it passes straight through, hits the fixed mirror down here, and reflects back up to the beam splitter. The other half of it reflects off of the beam splitter and goes up and hits a moving mirror in this tube. And this is where the real magic happens, because even though the light does just bounce right up there and hit this mirror that is currently moving down and reflect right back down to the beam splitter, because this mirror is moving up and down, it's gonna be at a different distance from the beam splitter than the fixed mirror down here, which means that when those two reflected beams of light come back together and recombine, there's going to be all sorts of wild constructive and destructive interference going on, because the varying wavelengths of light are no longer going to be aligned with each other. And because of that, we can do some pretty tricky math called a fast Fourier transform that allows us to essentially extract all of the individual wavelengths of light and figure out exactly which wavelength interfered with our object under test and which wavelengths were passing right through it. And so this is, I think, from a mechanical perspective, it's an incredibly simple machine, but from a conceptual perspective, it's a little bit difficult to wrap our head around. But hopefully once we get this thing fully up and running, it'll become a lot more obvious what's going on. So why isn't it fully up and running? It certainly looks like it is. I mean, the front panel here has LEDs showing all sorts of stuff. The mirror's moving up and down, the laser's on, the light's on. We should be there. And in the previous episode, we got super close. We had to align the laser because everything needs to be in perfect alignment on this thing, and we got the laser aligned, but we ran into a different problem that I think is gonna trip us up for a little while here. Let's spin this thing around and I'll show you what I'm talking about. There's some extra information that we need in order to get this interferometer working correctly, and that is the ZPD point, or zero path difference point. This is the point at which the moving mirror and the fixed mirror are perfectly equidistant to the beam splitter. That means that every wavelength of light passing through the entire optical path is going to be constructively interfering. As soon as that mirror moves away, we start getting into destructive interference and things get much more complicated. And then if we can actually detect how far away that mirror has moved from the ZPD, we can figure out which wavelengths should be constructively and which ones should be destructively interfering. And we have two tools at our disposal to do that. The first is a helium neon laser and the other is a light bulb. The laser is generated inside of this box right here. It has a very nice helium neon laser tube in it, and it goes through a beam expander to make a nice, perfect square beam of laser light coming out of the bottom. Then what we do is we chop out one corner of that light, so we end up with like a little L shape. And we fill that corner that we just chopped out with light from our little light bulb over here that bounces around into a prism. that passes through the entire optical path and then comes back over here and gets detected by this little board on the back that has 6 sensors on it. 5 of those sensors are within the laser light. And if we can get this board perfectly aligned to the laser, that 6th sensor is going to fall squarely in the visible light that's being generated by the light bulb. Now that goes through a massive op-amp chain and creates something called an interferogram. This is ultimately our goal here. And you can actually see it right here on the scope. The biggest peak is the point at which the 2 mirrors are perfectly equidistant to the beam splitter. And we have the most amount of energy striking the sensor on the board back here. But what's the laser doing? Why are we sending it through the path? Well, a helium neon laser puts out a very specific wavelength of light, which means that as it passes through the optical path and that mirror is moving, that wavelength is going to constructively interfere and destructively interfere and constructively interfere and destructively interfere over and over and over again. And we use that to create a beat pattern that tells us how fast the mirror is moving and when we need to take measurements. So by using this sensor board here, we've now figured out everything we need to have an interferometer working. But this one isn't working, and so what's going on? We're getting spurious pulses on the sensor that is detecting the light, the one that should be giving us our interferogram. Today, it's actually been pretty good, but in the previous episode, it was real nasty. So something on this board is unhealthy, and it's changed since the last time I was filming with it. The only thing that's changed in the room is that it's a lot colder today. So we probably have something on here that's going temperature unstable. It's gonna take a little bit of probing with the scope to kind of figure out exactly what's going on, because this is not right. Let's take it one step at a time here. The green trace should be the ZPD detection pulse, and it should be like 12 volts instead of the 0.5 volts shown here. But maybe this is just a probing thing. The test points on the laser detection board have a bit of corrosion on them. So after some scraping with the probe, I did manage to get a better connection. And there we go, that looks like it's supposed to. Something is still kind of wonky though, because the ZPD light goes on and stays on, and it shouldn't. And interestingly, after some time, I did manage to get some of that random noise to show up. And you can see it was enough to trigger the green trace here, but this only happened once and I couldn't get it to happen again. I'm really kind of at a loss here. So let's go back to the beginning and work on laser detection board alignment all over. Eventually I did get it realigned, and if you want to know how I did that, check out the previous episode. But that really just put me right back to where we were at the beginning of the episode. The last thing that I can think of is that Mike and I chatted about the ROMs on the microprocessor board. So let's check those. Fortunately, among all the documentation Mike hooked me up with, there was this service bulletin type page that talked about ROM revisions. My ROMs are IEK8000Ls, and if I look back at the documentation, those are for the DA8, which is physically the same unit but has a very different computer setup. I need IEK 5600 or IEK 6300 ROMs for my DA3. And fortunately, Mike sent me some spare ROMs along with the machine. These are IEK 56141 ROMs, which sounds close enough to me. Let's pop the DA8 ROMs out of their sockets, and by the way, extra kudos to Bomem for putting every IC in a socket. As someone who repairs old computers all the time, serviceability like this is a godsend. After popping the new DA3 ROMs into the sockets, let's fire the machine back up and, look at that. The ZPD light is going on and off like I think it should be. The mirror is going up and down, we have alignment, I'm seeing a clean interferogram from the little light bulb, and I'm not seeing any noise. Not only that, the mirror is now no longer going the full distance of the tube. It's turning around and coming back down much earlier, which is what it's supposed to be doing. But the way in which the ZPD light is blinking doesn't make much sense to me. So I sat down and traced out when it was turning on and off in accordance with the mirror position. I don't know what's going on, man. Like, I didn't fix anything, and yet the machine appears to be fixed. Even before I changed the ROMs out, this was looking pretty steady. And now that I've changed the ROMs out, I can't get it to misbehave at all, much less recreate the fault that we were seeing at the end of the previous episode where we had an insane amount of noise that was causing all sorts of problems. So, I don't know. That's just how it goes sometimes. The only thing I can think of is to push on with the rest of the build, and if the problem crops up again, then we'll troubleshoot it at that point, because I can't troubleshoot something that doesn't exist. So All right, so after swapping the ROMs out, the ZPD light started coming on and off in a pattern, and I made a little diagram here. I don't know if that pattern is correct. I mean, it looks potentially correct to me, but I'm gonna have to call Mike and ask about it. If that's all good, then that means that our laser's fully aligned, the white light for the interferogram for ZPD detection is fully aligned, and there's only one more alignment that we have to do to get this machine fully up and going, and that is the detector alignment on the front. And thankfully, Mike hooked me up with a bunch of documentation. This is just like one of 6 binders he gave me, and the detector alignment is outlined in here. So we're just gonna follow along with what it tells me to do, and hopefully we can get this thing fully ready to plug into a computer. All right, let's flip this thing back around so I can get to the detector on the front. Then we'll flip to chapter 14, DA3 installation, and skip ahead to the detector alignment section. I need to get access to the pre-amplifier board, so I'll just unscrew the 2 screws holding this cover plate on and then swing it out of the way. I then need to unplug the main harness to the pre-amplifier and then the preamp connection to the detector. Then I'll remove the 4 screws on the front of the detector box to gain access to the mirror adjustments below. Given that there are 10 screws in here for mounting and adjusting the mirror, I can already tell this is going to be a bit of a battle. First though, I got to get the detector itself out. I'll loosen up and remove the locking ring, then the detector just slides right up and out, and look at this beautiful chunk of wizardry. The detector itself is tiny. I'm guessing that the rest of the mass is just for thermal stability. And the detector looks to me to be an extremely high quality silicon photodiode. Pretty cool to see it up close though. But for this next step, we're going to replace the detector with this metal can that has a cross mark drawn on it. I'll just set that in the hole for now to protect the mirror while I get everything else fully set up. We want to be in mode 3, so I need to flip this switch from normal to test, and we want the visible light source, so I need to flip this switch for source 2. The light bulb kicks on after a few seconds, and finally I need to crank the resolution up as high as I can. Flipping this switch causes the iris under the source light to resize, and looking in through the detector hole, I can, for the first time, look through the entire optical path. Kind of wild to think that this view is going through so many mirrors, including the beam splitter. Finally, let's get that alignment can properly in place. I'll flip it around so I can push the target area down to the focal point. As I work the can down, you can clearly see the beam of light move into and out of focus. The goal here is to adjust the screws on the mirror mount until the beam of light is a perfect dot that is aligned dead square in the center of the cross mark. It's super fiddly work, but the visual feedback is immediate, which makes it a little easier. And hold the phones, the mirror motor is starting to make a weird noise now. Listen to this. It's a super faint sound. I had to boost the gain to max on that clip, but our spurious signal noise is back as well. Finally, the failure from last week is repeating itself. I'm betting that the mirror motor noise and the bad signaling are related. The laser detection board may be totally fine. Mike has warned me of the later revision mirror motor control PCBs before, and given that the motor noise and signal noise appear to be related, I think that's a solid place to start work. Fortunately, Mike sent me an older revision of the motor control board, so I'm going to do a straight board swap in this little box right here. Again, serviceability on this machine is top notch. Doing the board swap only took me 15 minutes, and that includes setting the camera up and hunting down tools. Once it's all back together, let's pop it into scan, and I held my breath as the mirror made its journey up and down, but it seems to be working perfectly now. I think we finally fixed our issue from the previous episode. That's awesome. Okay, that was a way easier fix than I was expecting, so let's get back into detector mirror alignment. Ultimately, I think I got it there. It's super hard to film because if I adjust the camera so the dot is visible, you can't see anything else. And if I bring the brightness up, the dot blooms out to be this huge amorphous mass. But in person, this looks absolutely spot on. Once I've got the mirror all locked down and tight, let's get the detector back in place. I'll slot it in roughly to where I think it should go, then plug in the preamplifier board and finally plug the detector in. The manual mentions the signal out BNC connector on the top of the machine, so I'll plug a cable into that, then hook my scope probe up to that output. Now I need to adjust the height of the detector such that the photodiode is perfectly on the focal point of light, but the signal out on the BNC connector is showing nothing. I don't think I understand what the manual is telling me to do though. It mentions using a light chopper to create a square wave, and I don't have one of those. It also mentions an alternative method, but I tried that to no avail either. I'm gonna have to get clever here, I think. Let's hook the scope probe directly up to the detector output. As I move the detector up and down, I can see the output on the scope moving between 0 volts and negative 15 volts, which, I don't know, might be right, might not be. If I pop the scope over to normal, as I pass through ZPD, I do get something that looks like an interferogram, but I have no idea if I'm properly in the focal point of the light. All right, nothing's going according to the manual, and I don't know if that's because the manual is not very well written, or I'm not smart enough to understand the manual, or something is still actually broken on the machine. It could be any one of those or a combination of all three, but I am noticing some strange behavior. The first is that the manual says to go ahead and set this thing all the way up to 5, but if I set it at anything higher than 0.05, I lose my alignment light here. There's apparently so much light coming out of the source that it blasts whatever's necessary to grab alignment. The only reason that I can get it to 0.2 right now is that I have 2 little mesh discs to attenuate the light going through the iris. And even with 2 of those attenuating the light dramatically, you can see that we're still flirting with alignment and the alignment light is going on and off. I have no idea what's going on here. That doesn't feel right to me. But I soldiered on anyways, and I should be able to detect something coming out of the signal out BNC jack on the top, but as you guys saw, nothing was coming out of that. So I went to the source, which is the detector down here, and I can get what looks like a real deal interferogram out of it. But near as I can tell, there's nothing on any of the test points on the pre-amplifier board down here, which means that maybe my pre-amplifier board has a fault. And so if the signal coming out of my detector never makes it through the preamp board, the computer up there is never going to see a signal and never be able to put anything out. Before we condemn the preamp board fully, it's far more likely that I just don't have a clue what I'm doing. Thankfully, Mike sent a bunch of schematics, and this is the one for this preamp board. On U1 here, in is the input directly from the detector into an OPA111 op-amp. The configuration looks like a pretty standard amplifier with negative feedback, but what's interesting is looking in the OPA111 datasheet, nearly this exact layout is shown for the detector on a CAT scan machine. Wild stuff to see this image in a datasheet. But I want to check input versus output here, so I'm going to put my probe on in and on TP1. Okay, I'm seeing what looks like a proper interferogram, but the amplitude is huge and it's offset deep into negative voltage, which means I'm not getting an output. That's not right. Okay, I wonder if it's being biased too low. The detector has 3 wires, ground, output, and bias. The bias is generated using an LM304 adjustable linear regulator to knock the incoming negative 24 volts down to a steady negative 15 volts. So let's move the probe over to the V bias pin on the detector. This should be at negative 15 volts, and sure enough it is. I can even adjust it up and down slightly using the variable resistor. Okay, something ain't right, but I'm still not sure it's not completely my fault. Let's check in and TP1 one more time, only this time I'm going to have the detector nearly all the way up, and I'm going to push it lower and lower. As I push it down, I can see the TP1 output of the op-amp increase from 0 volts all the way up to plus 15 volts, at which point the input from the detector goes from 0 volts all the way down to negative 15 volts. Then if I continue to push the detector down, the input signal comes back up and the TP1 output starts to go back down. Okay, this is absolutely an adjustment thing. I need to just get the detector aligned perfectly to the pinpoint of light. The way the manual said to do it wasn't working for me, so let's get creative. I put a small mirror inside the sample chamber, angled so that I could see the detector without blocking the light from the source. Then I pushed the detector down until I saw the light come into focus perfectly on the photodiode. It was fiddly work and even harder to film, but this got me surprisingly close. I was now seeing squiggles on input and output. So let's check the next stage. TP2 is the output of the next op-amp, so I'll pop a third oscilloscope probe onto that test point and look at that. we have a tiny interferogram on the input, an amplified version on TP1, and a massively amplified version on TP2. The next stage is the one that I was actually really worried about. The MN2020 is a wild, digitally controlled, programmable gain amplifier in a DIP package. Looking at the block diagram, it looks like a standard op-amp that has a built-in resistor ladder network that feeds into a multiplexer, and the feedback into the negative input can be selected via a binary address. Why on earth do this? Well, this gives the computer the ability to change the amount of gain on the fly, depending on front panel settings or type of detector or whatever, really. What a cool solution. But is it working? Let's get our probe onto TP3, the output from the MN2020. And looking at the scope, that is absolutely excellent. Perfect amplification every step of the way. That's exactly what I wanted to see. There's a lot of things that I'm still unsure of, but I think we're there. I think this thing is fully aligned. The laser, the entire optical path, even the sensor on the front here, it's all in perfect alignment. And as you can see, coming out of the pre-amplifier board here, I've got all 4 stages set up on the scope here. That looks to be like a perfect interferogram to me. That is awesome. And that's being output up to the computer up top here. And I think it's ready to go out from there into the PDP-1173 and have that start controlling this to do some real deal science. So what is left to get this connected up to the PDP-1173? Well, on top is a massive 50-pin connector, and that goes into a mega thick cable that goes down to this little board right here. Plugs in the back here, and on this side are a bunch of opto isolators. Now on the other side of those opto isolators, we have a 50-pin ribbon cable that's going to go to the high-performance vector processor. We have a 10-pin ribbon cable that's going to go over to the DEB41 as serial control. And then we have some external power. So I've got to make up some new cables to get this plugged into the PDP-1173 properly. And then I need to mount it because it's kind of weird and unwieldy just hanging out like this. And then we can plug this into this and we can fire all of it up at once and science? Profit? I don't know. I'm getting pretty excited about it though. So in the next episode, that's what we're gonna do. We're gonna try and get this thing plugged into the PDP-11 and we're gonna do real science like it's 1985. So I wanna thank you all so much for hanging out with me today, and I hope to see you in the next one.